Right, so hello everyone. Thank you to everyone who joined us for this series of the IMechE webinars, the Who, What, Why, and Where series. So this is your first time attending these webinars. These are monthly webinars we try to organize in the IMechE for PhD students as a way for reach out and present the latest research in tribology. So this is a great chance to just get an idea on what everyone's doing, give some advice, have some networking opportunities, and discuss the work. And if you are interested in presenting at one of these, the IMechE are currently looking for new presenters starting from March onwards. So if you are interested, please either email me, or if you look into the IMechE website, you will find an email on how to put your name up to be considered for the upcoming presentations. So today we have some very nice talks from some PhD students from Imperial and Glasgow. So first up, we have a talk from Jack. So Jack is a PhD student at Imperial College in bio-tribology and bioengineering project. His work is focused on the interfaces between biology and mechanical engineering to improve skin health. And I'm sure he'll give us a very nice talk now. So Jack, if you would like to lead the way, the floor is yours.
Thank you so much for that introduction. Can you see me okay?
Yeah, all good.
Okay, I'll start sharing my screen now. And can you see my slides?
Yeah, all good.
Perfect. Well, thank you again so much. Yeah, my name is Jack, and I'm a PhD student at Imperial College in Mark Mason's bio-tribology group, and also Claire Higgins' group in bioengineering in regenerative medicine. So what I'm going to talk to you about today is some of the work I did with collaborators from the University of Salford and the University of Southampton. And there's a kind of clinically held belief that we can train skin to be kind of more load responsive, more able to resist against deformation. But there's actually not a great deal of evidence about this. So we wanted to kind of challenge this clinically held belief and see how much plasticity there is within skin and how much is able to adapt. So we used quite a unique case where we've got lower limb amputations, and there we've got completely unspecialized skin. That skin's not meant for carrying bodyweight loading, and then the amputation or limb difference occurs, and then that skin then is required to be load bearing. So it goes from kind of being unspecialized to being able to do a specialized task. So we can really see how much adaptation is occurring. If we look at that limb case, we can see how much is adapted. So a little bit about lower limb amputees. So following a lower limb amputation, an individual's life changes forever. Thankfully, though, the development of the surrogate limbs has come on kind of leaps and bounds, and means that individuals with that limb difference are able to restore the mobility they have lost.
Sorry, Jack. I just forgot to mention, sorry, if you do have any questions throughout the presentation, please just type it in the box in front of you, and then I will be reading it out to Jack after his presentation. Sorry about that.
Perfect. Yeah, please keep the questions rolling in. Yeah.
Please.
Yeah. So these devices are able to restore the mobility they may have lost, and really importantly, has that kind of knock-on effect of giving people this independence. They can go about their daily living without having constant assistance or having to make significant changes around their lives. These modern devices now can do a lot of complex tasks, like walking upstairs and downstairs, things we take kind of for granted, but are very kind of complicated to program in. And you can see from this video, even, this is loose gravel. He's walking perfectly fine at speed. He doesn't look particularly taxed whilst he's walking, like it's significant effort. And some of these devices even can give a degree of tactile feedback. So, can inform him about what's happening to the slope without having to kind of use that visual guide. So this all sounds kind of very positive so far, but when we kind of look into the literature a little bit more, we find some kind of some stark injury statistics. So the device, really, to get that adequate function that we need quite a tight fit between the limb and the device to transfer that load whilst we're moving. Now, in order to get that adequate function, we're going to need friction. We need this friction to hold the device in place, and we get very comfortable in tribology of trying to minimize friction, as this usually improves efficiency. But in this case, kind of reducing the friction means that the device doesn't function as well. It slips, it comes off. But too high friction, and we know from the literature that if we increase that friction and that shear at the skin surface, we see a significant increase in kind of injury compared to if we just load it without adding that friction and shear. So when we actually look into the literature, we see that 75% of amputees using a lower limb prosthesis experience a skin problem. And that's 65% more skin problems than their able-bodied equivalents. So skin injuries are kind of a huge, like a disproportionate problem within the lower limb amputee community. And we see that this has knock-on effects in the NHS. We see 1 in every £150 spent in the NHS is spent on performing diabetic amputations. So these injuries can, especially in the diabetic population, lead to further amputations because the wounds won't heal. We also see that the amount of amputees within the globe is significant, and there's an amputation every 30 seconds globally. So this is a massive problem that affects like a significant portion of people, and it has multiple different effects. It's not just a case of skin discomfort and injuries. So we need to understand why this injury prevalence is so high in lower limb amputees compared to the rest of the population, and why is the skin not adapting like we think it should. And I think this is because we understand how skin can adapt on the soles of our feet and hands. And we're very kind of comfortable with this. We buy new shoes, we get the initial kind of pain and soreness, but then our feet kind of adapt to it. They become stronger. And we see that proved in the literature. People that run barefoot compared to not barefoot, they form thicker calluses in response to that loading. And then when we test the kind of mechanics of those calluses, we see they are stiffer than the equivalent sites on the kind of people that are running with shoes. But this kind of unique adaptability that we see on the sole of the foot it comes at a price. So that resilience to loading comes at the cost of slower wound healing. So we see wounds in feet take twice as long to heal. And so we've kind of got this library of information on how skin on the foot is able to adapt to loading, and then we're applying the kind of same logic to the amputee limb, but we just don't have this same information for lower limb amputees. So this kind of then raised kind of forced us to ask the research question, like, can amputee skin adapt to load like plantar skin does? And does this come with any trade-offs like it does with plantar skin? So what we then did was we recruited 12 lower limb amputees. And what we wanted to do was perform a range of measurements. So we want to see at different scales and in different modalities what is happening to that skin. So is the skin getting stiffer? Is the underlying biology changing? Is the actual structure and the architecture of the skin changing? So we performed a range of measurements on these lower limb amputees to try and understand what was going. And all of these measurements were what we call in vivo. So these were living people having measurements taken on their skin without removing it from their body. So you get kind of rich information, but it does come with the cost of kind of biological variability and things like that. So as a starting point, we wanted to see, is skin on the lower limb amputee just generally more stressed than the intact limb? So what we did is we wanted to look for a range of markers of inflammation. And what we found was that without having anything happening to the skin at all, that skin on the amputation surface was more stressed. However, these differences were quite slight, but across the range, skin on the amputation side was chronically kind of inflamed compared to it, but these differences were small. Next, we definitely understand that skin can thicken in response to loading, so we wanted to see if that was occurring as well. So when we look at the amputated limb versus the intact limb, we see there is a slight increase. So we've got a 1.6 micron increase in that outer layer thickness. But this difference is not significant when compared to the total depth. And when you compare that to actually the size of foot skin, it is orders of magnitude different, where that layer can be in the range of 750 microns. So a 1.6 micron increase is really not going to create the effects we want to see. We're also using an imaging technique. We wanted to measure to see how the roughness on the skin surface has changed. We saw a reduction in the kind of this apparent roughness that we measured, suggesting that maybe there was kind of abrasion occurring, creating a smoother contact, and hopefully this would lead to lower friction. But again, these differences were fairly minimal when compared across the whole population. So next, we wanted to understand the kind of underlying biology. So we looked at that kind of epidermal layer, and what that barrier, layer of skin really does is act as a barrier, and it protects us from protects the underlying tissue from the outside environment, but also keeps important kind of nutrients and things like that within the body and doesn't let them out into the external environment. So what we see is that kind of outer layer is, if you imagine a kind of brick and mortar structure, and the mortar is kind of made of fats, and they really help control the movement of water. And we see that at that kind of superficial layer, really close to the skin surface, we reduce the layer of the amount of lipids in the amputation site, which means skin's going to be almost more porous and more unable to control things coming in and out of the skin and how to distribute water effectively. And when we look at natural moisturizing factor, which is really important for holding water at the surface of the skin and pulling it from the external environment to keep us the skin well hydrated, again, we see reductions at the surface. So whether that be through kind of friction and abrading away these compounds, or whether it is a case of altering the underlying biology and that having knock-on effects, and then this kind of entering this cycle of disrepair. And then what we see is the knock-on effect of our inability to hold on to water and distribute it effectively. We see that water is then in too high of a quantity near the skin surface in the amputated limb. And we know from the literature that water exposure near the surface further leads to barrier disruption, breaking down of those lipid structures, and again is going to increase skin permeability. So what we're seeing so far is that we've made some changes in terms of increasing skin thickness, but we're degrading the biology. The skin is inflamed. We've got barrier disruption, and we're most likely got a more permeable skin, which again then is going to feed into the inflammation problem. So we've got a slight adaptation, but it's come at quite a significant cost, and the skin is actually probably degrading overall. But now we've got this kind of information, we want to then try and link that all together and understand what's happening with the mechanics of the tissue. So ideally, we'd see stiffening. Maybe the skin was more able to resist deformation, was less likely for the cells inside to be overly stretched or distorted, leading to kind of cell rupture and then death. But we see decommissioning of the tissue, and we see a 64% reduction in stiffness of the amputated limb. And then again, when we compare that to the foot, we see significant decreases and roughly 2 times softer than the heel. And then when we try and compare then to friction, we see that 21% increase in friction in the amputation site. So we've got a impaired biology, a softer contact, and we've got higher friction. So it's all kind of starting to make sense now why we see such high injury statistics in the literature. And we think potentially the mechanism causing this increase in friction is either due to a loss of those kind of lipids and natural moisturizing factors at the surface, kind of leading to a loss of that, maybe potentially a lubricating layer, or more likely is that the water being distributed higher at the surface has a plasticizing effect on the skin, softening the skin. That softer contact then leads to kind of higher skin buildup in friction, causing the increase in friction. So to kind of sum up everything we've seen so far, we kind of set out to understand what adaptations were occurring, and we see that some adaptations are occurring. The skin does respond positively. It increases that outer layer thickness, but the rest of the adaptations occurring are not beneficial for the amputee and would lead to chronic inflammation, problems with regular biological functioning. We're seeing a reduction in important mechanics in that contact. So we're seeing a reduction in stiffness and higher friction. And I think that then leads us next to people have done a lot of work on developing the devices. And then as engineers, we kind of focus in on the controllables. But there are 2 aspects to this coupling, and that's the skin and the prosthetic. And I think it's the solutions need to come in a skin side. So we need to be reversing or improving the skin beyond these degradation effects, and hopefully pushing it to the improvement to make skin more resilient and more like the skin on the sole of our feet. So product development is not the answer. I would just like to say thank you to a lot of people obviously contributed to make this project happen. So thank you very much to these. There was significant help with funding the project. So I'm happy to take any questions now, and please use these contacts if you wish to ask a question outside as well. Thank you very much.
Thank you, Jack, for that very interesting talk. So to our attendees, if anyone has any question for Jack, just please type it along and I will speak it out to him in a moment. So one question we have now is, has there been any studies in compatibility stiffness or compliance between the skin layers and the prosthesis materials? So I suppose the foot planetary skins are subject to both compression and shear tractions. How do these loads compare to those experienced by the amputees?
Yeah, so really, really interesting question. So there's two things. When you analyze people who run barefoot, you see that you can actually have about 100 times the pressure through that kind of strike of running without any breakdown. But when we apply these loads to tissues that aren't found on the bottom of the heel, we see significant breakdown, and that's not just in amputees, that's bed-bound or wheel-bound individuals as well. So the skin is just significantly so different in almost every metric you can imagine. But there's a type of amputation where you take the skin from the sole of the foot and you actually coat the surface of the amputation site with it. And when people have that kind of amputation, they are able to walk on the end of their limb almost immediately. They have very little skin problems afterwards. So when you use that as a loading site, the injury statistics almost inverse. But the usual cause of amputations are things like trauma or diabetes, which means the quality of skin is usually quite poor. So this then doesn't become a feasible solution, and using the kind of remaining leg skin is what happens.
So just as a follow-up, so then when they do attach, like you said, the skin from the bottom of the foot, then does that have like a time issue as well, or does it degrade like with time compared to normal amputee skin, or can it survive like the whole?
No, yes. So the skin is actually very resilient, and it has some cells within it that, regardless of where you place them in the body, they will continue to tell the cells around them to produce important proteins that lead to that kind of thicker, stronger skin that you find on the base of the skin. So transplanting that skin across has, the kind of benefiting effect, and then you don't have the degradation because these cells continue to think they are on the kind of sole, and they'll just keep producing it until that that person is person dies.
Interesting. So another question we have, where the removed limbs has salvageable skin on the plantar foot, they're sometimes used to close the residuum during surgeries. Have you found anyone in this population you can test to assess against your research?
Yeah, no, that would be the kind of golden ticket. But as I said previously, the kind of reasons that you have an amputation don't lend itself well to having that kind of amputation, because usually you have diabetes, which means your quality of skin is very poor, or there's been a trauma incident, which means, the kind of, again, the quality of plantar skin that may be left might not be enough to kind of cover that end-bearing surface of a thigh. But the studies that have been done on it, they've not been engineering focused, they've been medical focused, but in the kind of follow-ups with injuries and kind of anecdotal things about being able to tolerate pain on that limb, that it's almost the inverse statistics.
Yeah. And just received a follow-up from the first question. So it was being asked, can we change the interface stiffness between the amputated side and prosthesis by changing the compliant prosthesis materials?
So I can. That's what I'm working on at the moment. So that'll be for next time, I'll have to say. So I'm doing it via biology rather than via kind of engineering processes. But yes, you can.
I think also another question I had. So when you talked about the lubrication that happens in the system, natural moisture in the skin, does that include just moisture that exists already in the skin, or does sweat become a factor?
Yeah. So you can have kind of water and sweat, but you naturally produce these kind of moisturizing factors, and you also produce something called sebum, which is the kind of oily substance on the surface of your skin. But you need a hair gland to do that, so that only works on skin that's not from your hands and feet. So we're still thinking about how that affects lubrication. My supervisor previously has done some work about the components of sebum and how they influence it, and whether if you take out kind of fatty acids and things that the skin is naturally producing, what effect that has on friction. But that is something that's kind of still ongoing.
Well, another question from my side. It's a very interesting topic. So when you look at skin changes after the amputation and so on, is there usually a time frame? For example, does after like a couple of years or so on, it changes and then it just like saturates or becomes steady, or does it always change until your last day, like forever?
Yeah. So what will generally happen is obviously post surgery there might be some kind of plasticity, and generally through the day the limb changes shape a lot. It will just naturally kind of swell, and so that is a massive problem for amputees because they get custom molded sockets for the size their limb was at that point that it was taken, and then their limb changes by say 40% every day, and it no longer fits from day to day. But there was some work done in Southampton that found kind of post amputation there is a significant kind of softening of the limb, which kind of supports the data that I've got, and they found that the actual muscles deeper within the tissue, the fat kind of ingresses into it, that kind of causing a softening of the entire limb. So we're seeing this kind of degrading over time, which I imagine would eventually kind of level off. But yeah, the kind of outlook looks as if the skin and limb as a whole kind of decommission as a result of continued prosthetic wearing and use.
All right. Yeah. Thank you for that, Jack.
No worries.
Does anyone have any final questions they want to type for Jack? Right. If not, so thank you again, Jack, for the very nice talk.
Thank you so much.
Pleasure having you. So next up, we'll have Ulvis. He graduated from the University of Glasgow with an IMechE in aeronautical engineering in 2021. His final year IMechE project involved extracting random rough surface parameters and then generating new versions of the rough surface in MATLAB using those parameters. He started his PhD in the areas of triboelectricity and flexoelectricity in October 2021. And his project is focused on using contact mechanics to help explain important phenomena in triboelectricity with the applications for triboelectric nanogenerators. So again, if you have any questions for Ulvis during the chat, please feel free. You can type the questions as the presentation goes along, and I'll read everything after Ulvis has finished. And yeah, Ulvis, the stage is yours.
Thank you, Mustafa. So I'll share my screen in a second. I hope you can hear me just fine.
Yeah, all good.
Perfect. Okay. Right. Okay. My presentation will get a bit technical, but I'll start with background, with some background in contact electrification. So, as you may well know, contact electrification is a very well-known phenomenon, and many of us have experienced it when we get zapped by making contact with a rug or by rubbing a balloon against our head, against our hair to make it stick to various surfaces like this background shows. But the natural question is, why do things charge when they are put into contact? The observation that I do is very elementary and very old. The ancient Greek philosopher Plato mentioned it about 360 years before Christ. Yet the phenomena is baffling in many ways and resists being comprehensively understood in any simplistic way. So, why do dielectrics charge when they are put into contact with other dielectrics or semiconductors and conductors? I've created a basic diagram showing the goal and the basic process that is similar to my own research. So first of all, we select some contact problem, then we create a computational model. That model is the expected charging behavior. And this is the model that goes into this black box. And then finally, we compare the output of our model with empirical results to see if the theory is any good. And we can measure the charge density distribution and the surface potential using Kelvin probe force microscopy. But here are already some basic things that current research struggles to address. For example, what is the species that transfer charge? The initial suspect may be electrons. Maybe that electrons carry the charge. However, there is evidence of observed ions being transferred. It has also been found that rubbed surfaces can transfer material from one surface to another. So those are 3 options already. Then moving on to the popular triboelectric series, first published in 1757 by Carl Wilke. It has been used extensively to determine the direction of charge transfer empirically by rubbing pairs of materials, and it's still used to this day. However, equally careful and legitimate researchers have found different ordering using the same materials. Moving on, charging also depends on surface morphology. So a rougher surface would not charge the same way as a smoother one. Also, triboelectric charging relies on the input of mechanical energy. So things have to move and clash, and the process is intrinsically dynamic. So the frequency and the force of contact also play a role. The point is that despite the simple observation of contact electrification, explaining what we see is surprisingly complicated. And while all of that is interesting, it is much beyond the scope of one PhD, so a recent promising research focus was selected. My research focus is on flexoelectricity. It's a general effect that occurs in all dielectrics, and it has been proposed to play a major role in this black box here. So we come to the purpose of my research, which is shedding light on that black box. I select a very well-known contact problem in tribology circles, the Hertzian contact problem. The right figure is a graphical illustration showing a parabolic indenter contacting an elastic half-space. Because the problem is symmetric, only half of the parabolic indenter is plotted. I further isolate only one contact electrification mechanism, flexoelectricity. Flexoelectricity is by no means the exclusive phenomenon that produces contact charging, but with some recent research, it is proposed to play a major role, even reversing the sign of charge due to other mechanisms. For example, the difference in work function in materials to which triboelectricity is often attributed. So I'll touch briefly upon flexoelectricity, which is a combination of a material property, namely the flexoelectric coefficient, and a mechanical effect, the strain gradient, characterizing the change in deformation of the material over space. While the strain gradient is a third-order tensor and has an unwieldy 27 components, the flexoelectric coefficient is a fourth-order tensor and has 3 times more at 81. But it is possible to shoot 2 birds with 1 stone with some simplifying assumptions. So first of all, if we assume that the material is isotropic, that is that properties of the material do not change when measured in different directions, it would give the first simplifying equation for the flexoelectric coefficient. And secondly, if we assume that the flexoelectric coefficient has similar diagonal components, and we do some index notation mathematics, we arrive at the simplified equation we see on this slide, where we have a complex interaction of multiple components of strain gradient and a scalar flexoelectric coefficient, giving the polarization in z direction, which for various reasons is the only direction we are interested in for now. So why do we choose the Hertzian contact problem? It's because flexoelectricity is linearly related to strain gradient. We need to get strain gradient fields somehow to go further. For that, we need equations. The simpler, the better. And the parabolic indenter on flat is a very well documented and well understood contact problem. What is more, it is used to approximate stresses and strains created by atomic force microscopy tips. And it's also used in statistical analysis of rough surfaces like the Greenwood-Williamson model. The point is that it is a great choice for building upon. And also, you might have noticed the word half space. The half space assumption means that the indenter is indenting an infinitely wide and deep surface. In other words, there is only one boundary, which is an infinite plane. This is a simplifying assumption, but it can be used experimentally as long as the indented surface is deep and wide enough. And for our purposes, this formulation right here is ideal. You can see one of the 27 strain gradient components plotted on the side. These are the strain gradient contours within the half space. So we move on to deriving the equations, and I'll broadly describe the process. So no one provides the Hertz strain gradient equations directly for the simple fact that they are very unwieldy. Some of them are a page long. I have filled the background of this slide with one of these equations, and the diagram shows the steps for getting strain gradient for getting to the strain gradient equations. So we start with the stress equations in a very particular form that is helpful for the process. Then we differentiate them to get the strain gradient equations. The reason why the diagram says bulk is that singularities occur within the highlighted areas here when the equations are differentiated with respect to z. So each of these areas must be treated separately because taken by themselves, the equations only give results in this striped area. And they fail on the symmetry axis and on the surface within the contact radius, which is symbolized by the letter A. For this reason, the next step is performing asymptotic analysis to get the full equations. The final results are not shown here as they are not published, but once that analysis is done, we have the full stress gradient equations. And the final step is to use Hooke's law to get the strain gradient equations. All right, the maths is nice and all, but what is happening conceptually? How does flexoelectricity produce charge at the interface? This is a battlefield of an area, but the basic physics should go as follows. In this figure, a lot is going on. The indenter is shaded with red lines and the half space with gray lines. The figure describes how the charge transfer happens. The pluses and minuses represent charge densities, and the thickness indicates magnitude. All of these charges are surface charges. The pluses and minuses without the circles are ones produced exclusively by flexoelectricity. This is the so-called bound charge, and it cannot go anywhere and will disappear as the indenter is lifted. Now we move on to the triboelectric charges. If you remember me talking earlier about the mystery of the charge carrier, well, I will shamelessly say that I can at best guess what the exact species or what combination of species make up the triboelectric charge, but it is a fact that it appears. Now, I'd like you to turn your attention to the vertical dashed lines and the gap indication of 0.2 nanometers. It indicates when or where there can be no longer any charge transfer between the surfaces. The two surfaces must be close enough for charge transfer. Strictly speaking, nuclei of atoms never touch, except maybe in fusion, but if the device is doing that, then something has gone wrong. The maximum gap size we see here should be about 0.24 nanometers for free electron flow. That is, the atoms must be in the repulsive regime, though there are higher reported values. There is evidence that electron transfers that the electron transfer happens only in the repulsive regime. And all of that is the basic information needed to understand what happens in steps 1, 2, 3 in the inset and how the full larger picture is formed. First, we are selecting one particular area of this graph where the gap is small enough. And starting with bound charges in the half space that is right here, generated due to flexoelectricity, we notice that because the indenter is rigid and has no strain gradients itself, its bound charge here is not generated by flexoelectricity. Instead, the polarization generated in the half space pierces through the small gap and produces a bound charge equal and opposite side on the indenter. So now, in this first figure, we have an electric field that is not zero at the interface. If possible, and this is the second point, if possible, this electric field will want to tend to zero, the lowest possible energy state. And this is where the triboelectric charge appears and balances out the charge density in the area, certainly producing an electric field of zero. So now if you count the pluses and minuses in the larger picture, we have a perfectly balanced charge in the small gap area. Additionally, it has a distribution with the charge density increasing towards the center. Okay, so keeping our final goal in mind, we've talked about the Hertzian contact, what it is. We've talked about flexoelectricity. Now we'll talk about how we can find these, the charge density distribution and the electrostatic potential distribution. Thankfully, the surface bound charge is relatively simple to calculate, and it is just a dot product of the polarization with a normal vector sticking out of the surface. The charge density distribution could serve as an input for the following step, finding the potential. This step is not so straightforward, and I'll only give a brief explanation. There are multiple ways to calculate the potential. The equation on the screen is not my own work, but it is elegant and efficient. So R and Z are the points we want to solve charge density at. And rho and G are the points where our charge density is found. K is the elliptical integral of the first kind. And this equation is helpful for understanding the next slide, because rho, so where the charge density is found, might not reach as far as R, which describes the whole domain, the radial direction of the whole domain. Okay, so we come to the final result. And all that hard work produces this figure. You can see the charge density distribution. So that's this red line, and the surface potential distribution, the blacker line, plotted on the same graph. The reason why the charge density line only reaches to 10 millimeters, while the surface potential reaches beyond, is because of the equation on the last slide. The charges have an effect far from where they are located. In addition, it only reaches to 10 millimeters because that was the maximum contact area. Outside of this maximum contact area, nothing could have charged because the gap is too large. And so we complete this picture. And my research takes further interesting steps, but it has not been published yet. So I won't mention them. However, now you know something of the physics and the principles of how flexoelectricity can produce charge and electrostatic potential. So thank you for your attention, and I cannot take the credit for this. I've had a lot of help in my own research, though I don't write any names here. So please ask your questions now.
Thank you, Ulvis, for the very nice talk. So do any of our attendees have any questions for Ulvis? If you do, just type it into the chat box and I'll read them out. So one question we have, the chemistry of the contact materials, contact stiffness, and the surface finish might be important to triboelectrical effects. Does the relative velocity have any effects too?
Yes, so it does, though my own research does not touch upon that, but I am aware that it has an effect. I couldn't tell you much about it, but it would have an effect, yes. Because there's a difference between, for example, charge relaxation in metals and the mechanical. It's just that they happen at different time frames. So the velocity, the frequency would affect things.
Yeah. So one question I wanted to ask. So you're looking at rolling conductivity, RCF conditions or rolling conditions. Is that right?
Could you repeat that, please?
Is it rolling condition?
Oh no. So I'm looking at indentation. So just indenting.
Okay. Okay. So the charge density that you had, so you had it being higher in the middle. Is that just due to the stress distribution in this case? Or
the stress gradient distribution, yes.
The stress gradient, yeah.
Yeah.
Okay. Yeah.
And also important, the point, the why it's higher in the middle is because I only plot half. So since the program is symmetric, you would see the other half being the same. It's just saying.
So not quite. So I don't have like much experience on flexoelectricity, but how does that compare in terms of like in real life applications? Do you get damage? Like I know like leakage currents and like EV applications and so on, they could have detrimental effects. Does flexoelectricity also play a role in that?
I wouldn't be sure, but I do know that there's research. I could quote the paper if you're interested. There's research that shows that it does compete strongly with more classical effects. You might have heard of triboelectrification due to the work function difference. There is research that shows that flexoelectricity can even dominate that, which is normally considered a very strong effect. But so with regard to that, your question, I'm not so sure. I would assume so, but I don't know.
Right. So another question we have: what is the current state of experimental testing of flexoelectric currents? What would you say?
Current state of testing of flexoelectric currents. Well, I would say I'm not sure how to answer that question. Well, the research is not very mature. Though flexoelectricity has been researched for a long time. In application into this kind of application, it's all quite new, and so I suppose there's a lot to do still.
So have you done any experimental validation then for your theoretical work?
No, but the hope is that I'm working in parallel with some other PhD students, and they're focused more on the experimental. I'm doing the computer modeling bit. So hopefully there will be actual validation. However, there are papers that show the same trends I find. So you wouldn't find the trend that I showed in the last slide because there are more steps you need to take to get the final trend. But there's some backup, experimental backup to my model.
Yeah. So there also what materials are you testing?
So since this is not experimental, so the material selection, I've tested PMMA, which is I just input, even though some of the simple kind of assumptions would not apply. I've tested with PMMA, I've tested with titanium oxide, and with some other, and with other, well, titanium oxide, not polymer, but also with other polymers.
Okay. Yeah. Does anyone have any other questions for Ulvis? No. So so one question I had as well. So I know you've chosen the elliptical contact mechanism or so on. Are you going to or planning on trying different geometries in the future, or would you say it's transferable as is, or how do you think it might compare to different contact geometries?
So I probably won't try different geometries in the future, but it is there are natural extensions. So, for example, in what how with the assumptions I'm working right now, I'm ignoring any friction. I'm ignoring adhesion, but both of those effects make an impact. So maybe the next step would be adding adhesion and friction. Also, there are statistical approaches that use the Hertzian contact theory. So it and for rough surfaces, which might be more realistic. So that's also a natural next step using what I've produced right now for some statistical approach. So as I mentioned, this Hertzian theory fits well into it lends itself well to further research. Let's put it like that.
Mm-hmm. That's so we'd be thinking of including like asperity contacts and so on, like stress points from asperity contacts. They
Yeah.
might create changes in the distribution or so on.
Yes. I would be doing things like that. That's the hope in the future. For now, it's more basic, but yeah.
Okay. Thanks, Ulvis. I think we do have one other question. So, do electrical wires or circuits experience these triboelectric effects? So, I'm thinking loud about computers and microcomputers used in aerospace vehicles.
That's an interesting question. Well, it depends. If you have wherever you would have a dielectric, so an insulated wire contacting another insulated wire, so you would it might be completely negligible, but you would have this effect. You would have the flexoelectric effect because it occurs in all dielectrics. So it might not be worthwhile worrying about it in that kind of aerospace application, but I mean it would happen.
No, but still, like in terms of practical applications, still a working area to see how important or how much need there is to look into that.
So the application, one of the primary applications would be nano generators, so triboelectric nano generators, and this is one proposed mechanism of how the triboelectric nano generators might generate power. Also, low power devices, sensors, and things like that. This is excellent. This would be an excellent self-powering mechanism, reducing the need for batteries and so on. So those are some practical applications for this.
Yeah, it's very interesting. So thank you, Elvis. So if no one has any other questions, we'll just thank Elvis again for the very nice talk.
Thank you.
And yeah, you can always contact Elvis from the IMechE, the program sheet, if you have any other questions you want to ask him. But yeah, I think that would conclude today's webinars. So like I said, we are currently looking for more students who would be interested in joining on from May onwards. So if you are in general interested in presenting in one of these, you don't have to pick a month out right now. You could just send us an expression of interest and we will discuss with you later on how to include you in our webinar series. So if you are interested, you will find the email on the IMechE Tribology Group website. So you could just email and say, hi, I'm so and so on, and I want to join. And we'll see what we can do. So thank you everyone again for joining, and we'll hope to see you all in next month's webinar, which will be on the 8th of March. And we will be sending out updates soon. So yeah, thank you everyone. And yeah, we'll see you next month.